set B is a complement of A. So each and every element has a complement in that set. Therefore, power set of X less than or equals to is complemented lattice. So power set of less than or equals to is complement. And then another notation is that we can see that power set of X star ring sum complemented 0 1 is complemented lattice. Now this notation says that power set of X has a star and ring sum, right? Complement for C and 0 1. This C denotes a complement. Here we can say that A complement is equals to B, because B is said to be a complement of A, and this is a notation we have in PPT also, that is A dash is equals to B. So that is another notation, A dash is equals to B. Now next is distributive lattice. Distributive lattice means lattice L star ring sum is said to be distributive lattice if it satisfied distributive laws. Distributive laws means star is distributive over ring sum and ring sum is distributive over star. Now in this one what we need, distributive laws. Now one more thing is that there are two definitions for lattices. One is power set of lattice L comma less than or equals to is lattice. Another one is L comma star ring sum as a lattice. Now these two definitions are equivalent. In this definition is a lattice with a poset, and this definition is said to be a lattice as an algebraic system. Algebraic system means that star and ring sum, these two are binary operations on L, and they satisfy three conditions. Star and ring sum should be commutative, star and ring sum should be associative, and star and ring sum should satisfy distributive law, or we can say that it satisfy absorption law, right? So these two definitions are equivalent. That means if we suppose one definition for poset, then we can prove that definition that L is less than or equals to a algebraic poset. That means we have two binary operations, star and ring sum, on the set L. And if we assume that L star ring sum is a lattice as an algebraic system, then we can have a relation less than or equals to which satisfy three conditions: reflexivity, antisymmetricity, and transitivity. So these two definitions are equivalent to each other, and therefore we have taken in a distributive lattice L star ring sum as a L star and ring sum lattice as an algebraic system. Now next definition is Boolean algebra. That is our topic. Now Boolean algebra is a lattice which satisfy two conditions, that is that lattice should be complemented lattice and it should be distributive lattice. Now in a complemented lattice we need a bounded lattice, so therefore here we can say that any Boolean algebra is a bounded lattice, it's a complemented lattice, and it's a distributive lattice. So there are three conditions for Boolean algebra. We need three definitions. Now in a Boolean algebra we have lattice. So lattice have 3 to 4 conditions. First, binary operations should be commutative, it should be associative, it satisfy absorption law. Now bounded lattice means that lattice should have 0 element and 1 element in that set. Then complemented lattice that is for each and every element A there should be a complement of A in the set. And distributive lattice means star and ring sum satisfy distribution law. That means star is distributive over addition and ring sum is distributive over addition. Now let us take an example which we have already discussed, that is power set of X. Now here X can be any non-empty set, then power set of X intersection union complement phi X is a Boolean algebra. Here intersection is for star, union is for ring sum, complement that we have already discussed, phi is a 0 element, and X is the 1 element of Boolean algebra X. And we know that power set of X intersection union is a lattice as an algebraic system. That means intersection is commutative, intersection satisfy associative law, and intersection and union both are satisfy absorption law. So power set of X intersection union is lattice as an algebraic system. Power set of X intersection union is distributive lattice. That means intersection is distributive over union and union is distributive over addition. It's an easy exercise of a set theory that we have already discussed in standard 8 and 9th. so we are not going to discuss that part. Now next is bounded lattice. Bounded lattice means we have phi as an lower bound and x as an upper bound. In fact, phi is a greatest lower bound, that is GLB of power set of x, and x is LUB of power set of x. That part is already discussed. Next, complemented lattice. Power set of x intersection union C phi x is complemented lattice. That means each and every element of power set of x has a complement in set power set of x. Next is a example S6 star ring sum C01 is again a Boolean algebra. Here S star S6 star ring sum complement. S6 is nothing but a set of all divisors of 6, and here A star B is nothing but GCD of A and B, and A ring sum B is equals to LCM of A and B. GCD means greatest common divisor and LCM of is least common multiple. Now here we have S6 as an lattice. That means if we take S6 is equals to 1, 2, 3 and 6. These 4 elements are divisor of S6. 1, 2, 3 and 6. These 3 elements are divisor of S6, and we know that this GCD of any 2 elements A and B belongs to S6. Then A star B is equals to GCD of A and B. It should be in S6, right? So here star is a binary operation on S6, and here we can say that star and ring sum are commutative, associative, and it's satisfy absorption law. Now distributive lattice. Here we can say that star and ring sum are S6 star ring sum is a distributive lattice, because star is distributive over addition, ring sum, and ring sum is distributive over star. That is an easy exercise for GCD and LCM. Then we have bounded lattices. Bounded lattice means S6 has a GLB in the set S6, and S6 has a LUB in again S6. Now GLB of S6 is a 1 and LUB of S6 is a 6. Now let us see how GLB of S6 is 1. We want to prove that 1 is a GLB of S6. For that we need to prove 1 is the lower bound of S6, and another one is that if we have any another lower bound, then that 1 is the greatest element among all lower bounds. Now let us find out lower bound of S6. That is only a singleton set A1, because 1 is less than or equals to x for each and every x in S6. Right, so here we have only one lower bound, and therefore it is a GLB of S6. So here 0 element of S6 is nothing but 1. Similarly, we can prove that upper bound of S6 is nothing but a singleton set 6, and it is the only element, therefore LUB of S6 is a 6. So 6 is an one element of S6. Therefore S6 is a bounded lattice. Then we have complemented lattice. Now let us see what are the complements of elements of S6. Now here we have S6 is equals to 1, 2, 3 and 6. Now I will prove that complement of 2 is 3. Complement of 2 is equals to 3. For that what we need to prove? We need to prove is that 2 star 3 should be 0 element, that is 1, and 2 ring sum 3 is equals to 1, that is 6. Now 2 star C is GCD of 2 and 3 according to the definition of star, and GCD of 2 and 3 is 1 because the greatest common divisor is 1. 1 divides 2 and 1 divides 3. Similarly here we have LCM of 2 and 3 is equals to 6 because the LCM least common multiple of 2 and 3 is 6. So 3 is a complement of 2, and similarly we can show that 1 dash 6, that means the complement of 1 is a 6, that is GCD of 1 and 6 is 1, and LCM of 1 and 6 is 6. Therefore complement of 1 is 6. So here we have 4 elements, 1, 2, 3 and 4. Each and every element has a complement, and that complement lies in a set S6. Therefore S6 is a complemented lattice, and therefore S star ring sum 0, 1 is a Boolean algebra. Now next definition is homomorphism. Homomorphism of one Boolean algebra to another Boolean algebra. Here one Boolean algebra is B1 star ring sum dash 0, 1. Another one is B2 meet joint complement 0 tilde 1 tilde. Now these two elements, any function f from B1 to B2 is said to be a Boolean homomorphism if it satisfies these 5 conditions. And that 5 conditions are that f preserve star, second condition f preserve ring sum, third f preserve complement, fourth one f preserve 0, and last one f preserve 1. So here any function satisfy these 5 conditions, then that function f is said to be a homomorphism, or we can say that Boolean homomorphism from one Boolean to another Boolean algebra. Now let us take an example of that set. We have power set of x, intersection, union, complement, phi and x. This is our one Boolean algebra. Another Boolean algebra is that S6 star ring sum dash, that is complement, 0 element 1 and 1 element 6. Now we want to show that these two Boolean algebras are homeomorphic. That means there should be a function f from power set of x to S6, right? There is a function from power set of x to S6. Now let us define a function. One more thing. Here we need x should be set of two elements a and b. Now define a function f from power set of x to S6. Define f from f of phi is equals to 0 element, f of singleton set A is equals to 0 element, that is 1, f of singleton set A is equals to 2, f of singleton set B is equals to 3, and f of set AB, that is x, should be 6. Now these functions satisfy star and ring sum. That means if we take any two elements a and b from power set of x, then f of a star b is equals to f of a meet f of b. Here star means intersection, that means f of a intersection b is equals to f of a. Meet means here we have star f of b, right? For each and every element a and b power set of x, function satisfy this condition. Let us take a particular example. If we take a is equals to singleton set a and b is equals to x whole x, right? Then a intersection b is singleton set a intersection intersection x, and that is singleton set a, because it is an only element which is common to both singleton set a and x. This implies f of a intersection b is equals to f of singleton set a. Now according to the definition of function, f of singleton set a is equals to 2. So here we get that value is equals to 2. So this is our left hand side, f of a intersection b, and we get that value as a 2. Now we will prove that f of a star f of b is equals to 2. Now f of a is equals to we have f of singleton set a, and that is equals to 2, and f of b is equals to f of x, and that is 6. So here we have f of a star f of b is equals to f of a is equals to, we get 2 star f of b, that is 6. Now 2 star 6 is nothing but GCD of 2 and 6, and GCD of 2 and 6 is 2. So as a right hand side again we get two values. So here we can say that these two values are equal, and we can prove for any elements a and b from power set of x. Similarly, we can show that f of a ring sum b is equals to f of a joint f of b. Now f of a ring sum b is equals to f of joint b, means f of a union f of b is equals to f of a ring sum f of b, right, for any elements a and b of power set of x. So from these two conditions we can say that f preserves star and ring sum. Now next condition is that f of a dash is equals to f of a complement. Now here a dash, a is an element of power set of x and its complement is a complement with respect to x, universal set x. So let us take a is equals to singleton set a or singleton set b. Let us take singleton set b. Then a dash is nothing but complement of singleton set a b, and that is singleton set a. So a dash is equals to, we get singleton set a. Therefore f of a dash is equals to f of singleton set a, and its value is 2 according to the value definition of f. Now let us calculate the right hand side. Now f of a complement, that is equals to f of a dash, because in a S6 complement is denoted with dash dash. Now f of a, with value of f of a is b, singleton set b, value of f on singleton set b is 3 and its complement. Now 3 dash, complement of 3 is 2 in S6, that we know. So here we get this value equals, so f preserves complement also. Now next is f preserves zero element. That means we need to show f of 0 is equals to 0 tilde. Now this 0 is a zero element of power set of x, and 0 tilde is an element, zero element of S6. We know that 0 element of f is 5, power set of x is 5, and 0 element of S6 is 1.